1.6 is kind of fun because we get to put things in context using graphs, and we're going to actually use our calculators in class on Thursday. So make sure to bring your calculator to class on Thursday. You will want some ability to graph, even if you don't have a TI yet and you have an app on your phone that will allow you to graph. That will be useful in class. Ideally, you should be looking to get that TI ASAP though. So, the first thing that we'll talk about in terms of graphs is graphing things based on their verbal descriptions, which is really just, do what is being described, right? So if it's increasing, you know that it's going to go up as you go along the x-axis. And if it's decreasing, you know that it's going to go down as you go along the x-axis. This concept I don't expect you to have a lot of trouble with, but if you have questions, please send them to me. The next part your book calls graphing basic functions. I think they're more foundational functions because they're not simple. They're just, you see this a lot, so you want to get familiar with these kinds of functions. The first of which is a constant. So if you were given the function, say, f of x equals 2, this is a constant, right? 2 is just a constant. So your function is constant. When we plot this, if you were to take a data set, right, which is ultimately whenever you graph something by hand, what you want to do is write it out numerically, right? Write a data table. So you have your values of x and you have your values of f of x. Fill in the table. So say I started at -2 in x, and I want to go -2, -1, 0, 1, and 2. I like using these a lot because the numbers are small and they're relatively easy to substitute in by hand. So it gives you a good picture without having to do a lot of work, usually. But in this case, because our function is constant, it doesn't matter what x is, because there's no x on the right-hand side. So I just have 2, 2, 2, 2, 2. And then when I want to translate that into a graph, I can draw my axes. Here's my x and my y, or f of x. Right? The points, really that's still the y-axis, so I'm going to take that away. But so that's our y-axis, but the graph that we're about to draw, that is going to be our f of x. So if I draw in here a scale, so I'm going 1, 2, and then on the other side I'm going to need a 1 and a 2, and then if I go up, 1, 2, so this is y equals 2. So f of x equals y, remember? So when I draw the plot, make that purple, it's 2. It's 2 here, it's 2 here, it's 2 here, here, and here. And so then I just connect all of my dots, and that composes my f of x. So what you notice is that if you have a constant, it's just a flat line. It's parallel to the x-axis, actually, which we'll talk more and more about those sorts of concepts later. But generally, if you have a constant function, that's going to be written as f of x is equal to some c, where the c is any constant. It could be 2, like it was here. It could be 56. It could be -3.7. It could be any constant. If we take this to the next basic function, or as I would say, fundamental function, we can look at f of x is equal to x. Now in this case, whatever x value I substitute in is exactly what I'm going to get right back out. So if I build my data table for x and f of x, then if I want to go from -2, -1, 0, 1, and 2 again, when I put in my x values, then f of -2 is equal to -2. F of -1 is -1. F of 0 is 0. F of 1 is 1. F of 2 is 2. I get exactly the same thing back out. So if I go and I construct my axes, here's my x and my y, and then all the color fun stuff, 1, 2, 1, 2. My scale is not perfect. 1, 2, 1, 2. Then from here, if I want to plot in purple again, -2, -2. So -2, -2. -1, -1. 0, 0. It's being silly, I need dots. Dot, dot. 1, 1. 2, 2. And then if I go back to the line in order to connect these guys, then I have y equals x. Or, in this case, f of x equals x. That is your identity function. Because whatever you put in is exactly what you get back out. We can continue with x squared, and in this one, if I use the same data, -2, so -2 squared, this actually may require a little bit of showing you that. So -2 squared is going to get me 4. -2 times -2, 4. F of -1, -1 squared, -1 times -1, gets me a positive 1. F of 0 is going to be 0 squared, which is still just 0. F of 1 is equal to 1 squared, 1. F of 2 is equal to 2 squared, 4. And we can then again build our axes, x and y, construct our scale. So we have a -1, -2, +1, +2, and then along the y-axis we want to go from 0 to 4. So 1, 2, 3, 4. -2, we go all the way up to 4. And -1, we go up to just 1, 0, 0, 1, 1, 2, 4. And then we want to connect those guys. And it extends beyond that. So that gives you a rough parabola shape that you would work with for x squared. We continue with an x cubed. Again, we can evaluate the points. F of -2 is going to be -2 cubed, which puts us at a -2 times a -2 times a -2. Oh, okay, so that's -8. F of -1, we have a -1 cubed, so -1 times -1 times -1 gets us a -1. F of 0, 0 cubed, as many times you multiply by 0, it's still 0. F of 1, we have 1 cubed, getting us just 1. And F of 2 is going to be 2 cubed. 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. Right? So we have -8, -1, 0, 1, and 8. So this one is going to be a little bit more interesting in the axes because we need a bit more height. So our x-axis and our y-axis, and then if I convert to green, -1, -2, +1, +2, convert, oh no, I need to do y. 1, 2, 3, 4, 5, 6, 7, 8 is way up there. Alright. Purple, and let's make bigger dots this time. So I have, at -2, I need to go all the way to -8. So all the way down there. -1, I need to be at -1. That's not so bad. 0, I need to be 0. 1, I need to be 1. And 2, I need to be all the way up at that 8. And then I can connect those. So this has this curve to it, and then it goes up and continues on. Same over here, and continues on. So you get that curve. You can also graph this in your calculator to confirm that that's what it looks like if you're not familiar with it. The last one of these examples, square root of x. So this can be really important, right? We talked about before, if I try and evaluate f of -2, I have the square root of -2. That's not real. So we're going to say that that does not exist. If you're familiar with imaginary numbers, that's fine. We do not use them in this particular class. If you go on to college trigonometry, you'll use them there. But for now, we're solely considering real numbers. So the square root of a negative number, we will treat as though it does not exist, because it's not real. Okay? So f of -1, we have the same problem. Square root of -1, we're going to say that does not exist. F of 0, on the other hand, what's the square root of 0? It's 0. So f of 1, square root of 1, which is also 1. And finally, f of 2 is going to be the square root of 2, which you probably don't know that, but your calculator does, so you can always ask it, and it's, if I recall, about 1.41. Make that an approximate. So that gets us nothing useful for -2 and -1. 0, we know we have a 0. 1, we have a 1. And at 2, we're close to 1.41. So we can go and draw our axes, x and y. And we really only need to consider 0, 1, and 2 in this case. And then we can plot our data points. 0, 0. That should be, there we go. 1, 1, 1. And then at 2, about 1.4. What you'll find if you graph this on your calculator, you'll see that it connects and it sort of slows down. What it should look like is very similar to a parabola turned over on its side. In class, we will play with the calculators a little bit, so you want to make sure to bring it. We'll graph a bunch of stuff. We'll talk about the viewing window, trace, and figure out how to find an intersection of two graphs on your calculator. Okay? But the next thing that we'll move on to is to graph piecewise functions. The most important takeaway on piecewise functions for graphing them is that you're going to want to use a table of values. You're going to want to do this by hand. You're not going to want to implement your calculator, because your calculator is going to graph the whole function on the whole domain. So if you plot 2x and 3x minus 2, you're just going to get the full graphs for both, and that's not what a piecewise function is. The piecewise function, right, that I've given you in this example is that it's 2x whenever x is less than or equal to 1, and it's 3x minus 2 whenever x is greater than 1. Okay? So that's why you want to do a table of values. If we construct that here, we have our x and our f of x. Every data point that you use, so I want to make sure that I have values above and below 1. So I'm going to go -1, 0, 1, 2, 3. Because then 1's in the middle. Okay. At -1, -1 is less than or equal to 1, so I substitute that -1 in for x in the equation 2x. Okay, so f of -1 is given by 2 times -1. 2 times -1, that's -2. At 0, 0 is also less than or equal to 1, so f of 0 is going to be given by 2 times 0, which is 0. And then at 1, I want f of 1. Now, it's important to notice here that there's an equals in the first one, but there's no equals in the second one. So that means when x is equal to 1, I only look at 2x. So 2 times 1, that gets me 2. And then for the 3x minus 2, I can substitute in, that's for my f of 2, right? 2 is not less than or equal to 1, it's greater than 1. So I'm going to substitute that in. 3 times 2 minus 2 gets me 6 minus 2, which is 4. So 4 for the 2, and then the 3, f of 3. 3 is again also greater than 1, so I have 3 times 3 minus 2, which is 9 minus 2, or 7. So now I have an idea of how this is going to look when I have to graph it by hand. So I can construct my axes. I need to make sure that my y value gets high enough and low enough. So there's my x, there's my y. I have -1, 0, +1, 2, and 3 for my x values, and my y values go from -2 all the way up to 1, 2, 3, 4, 5, 6, 7. Okay. So when I go to plot the points, -1 is at -2, 0 is at 0, 1 is at 2, 2 is at 4, 2 is at 4, and 3 is up at 7. And then I can put these guys together. Not the way that we did before. This is the line. This goes from the -1 that I have in my data set up to the 1. And it includes it, so that is a closed dot. Now, what I need to determine is actually f just on the other side of 1. Because to construct the other part of this graph, I'm going to need to know what f of 1 is for the other part, which is the 3x minus 2. So that would be 3 times 1 minus 2, getting me 3 minus 2, or 1. So what I'm going to do there is, instead of having this big dot, I'm going to make an open circle at the point 1, 1. And that point is where this other part of the graph would be if it actually hit that point. So the red line continues off to the right because it's for all values of x that are greater than 1. And the purple continues off to the left along this line, okay, for the 2x. But it ends here. It doesn't go any further than that, because it's only defined for x values that are less than or equal to 1. And I had to draw the open dot because they're not the same, and the other function is only defined for values strictly greater than 1. Okay? So an example of a piecewise defined function that you're actually probably familiar with is your absolute value function. This one you would have seen written as f of x is equal to, right, we have those vertical bars around x. If you write this as a piecewise defined function, you're saying that it is -x for x values that are less than 0. And it is positive values of x when x is greater than 0. You can pick really which one is which in terms of which one has the equals, because they're both 0 there. So the reason that this one is different is that when you graph it, the two different sides here are the same at the point where they intersect. And so when you draw the graph, this doesn't have an open hole because they're both 0 at 0. And that gives you an example of how it can be continuous, but still piecewise. I can give you an application problem in class, but this video is already running longer than I wanted, so I'm going to stop here. See you in class.